Welcome back, and today's going to be the final lecture, and we're going to talk about multivariable control, also known as cascade control. So throughout the course, we've talked about more or less controlling one thing at a time. But in order to have more robust control, you might need to have more than one CV, or variable that you're controlling. So to do this, we're going to build inner and outer feedback loops, and this is going to really significantly improve our performance, as well as improving disturbance recognition and rejection. So think about our original heated stirred tank example. This allowed us to have some temperature coming into a tank, and then we identify the output temperature of the tank based on the fluid that's leaving. That is our controlled variable. We want to keep the temperature constant. To do that, we're going to measure and control the actual temperature. We're going to have some set point for the temperature of interest, so T set point. And then that's going to go into some percentage of an open or closed manipulated variable. So that's going to be our actual process valve. That changes the flow rate of the steam, something else, but accounts for any disturbances here. However, other disturbances might be examples of the flow coming in. So the flow, or even potentially the temperature, if this is not exactly constant, of the fluid flowing in, might also need to be controlled. So we might need to consider our control variable being the flow rate itself, in addition to the temperature of the system. And when they work together, they can be quite fast and effective, where the inner loop, or the secondary controller, is going to be even faster. Heuristic says about 3 to 5 times faster, but ultimately, by adding a second level of control, we can really improve the system's speed and performance. So let's design a multivariable. We're going to still be trying to control primarily the temperature. That's the main objective. But to do that, we will start controlling the flow rate here, which is set based off the temperature. So any potential disturbances to that flow rate, we're going to be accounting for to keep that really constant and make sure that we design a really effective system. So we have our inner loop, which is going to be the secondary controller. That's going to be the flow rate. And we have our outer loop of the temperature here. So how do we build that? Think about all loops in general. We are going to build it normally from this. We would have our set point coming in with some error related to the set point and the temperature we've measured. And then that's going to go into the process valve that goes into the process itself that then allows for disturbances to come in to give us our temperature out. We're going to do the exact same thing here, but we're going to have an inner loop and an outer loop. So we can start from either. You can start from the outer loop and then build in, but I'm going to start from the inside immediately. So we're going to have some new set point come in, which is our manipulative variable here. So I'm just going to have that come in, MV1 or SP2, if you want to call it. And this is going to involve some type of error as we have our own feedback loop in addition. But that's going to go into our flow controller. So I'm just going to call this GC2 or secondary controller. That's then going to go into its own valve of interest. But if there's no specific valve involved, then it would go in directly. If we wanted to just skip that and make the transfer function equal to 1, then that would yield our MV2. That would go into the process itself, but would be on process secondary control, because the process here is really talking about this, not the whole system right there. And in that process, it's going to go into some new error where we have to add the disturbance that comes in. So I'm just going to write it beneath because I'm at the top of the screen here and I don't want to miss out. So we'll have GD2 to discuss that disturbance that goes in based on the disturbance 2. I could write DV2, I could write D2, either way. That gets added together to yield out into the CV. This is going to be CV2. So this is our flow. Output of our flow entirely. Now the output of our flow is going to go into the process of the whole system because that flow is feeding into the actual system itself. So that'll be GP1. That gets added with its own error from disturbance. That's supposed to be a plus. Not my best. So that's GD1. Goes into there based on disturbance variable 1. And then that yields a full output, my CV1, which is my temperature. That is going to ultimately be read out by my system based on whatever sensor I have. So we'll call this a GM1 that goes to form my ultimate error. But notice there's still an error here of my initial CV that needs to go back. So that's going to go through its own process controller, GM2. And then I'm going to take this out to go into its own error that has to pass through its own controller back here. So before this MV, I'm going to have GC1. That's going to have an error function in. That then will lead to error function 2. That means that this has to have a plus minus here for my feedback with set point 1. So kind of complicated approach, but really what I did is I designed my inner loop, where the inner loop is going to be all of these pieces. Or my secondary controller, and where everything else involves my primary controller. And so to feed it in, we have our original set point into our system for temperature control. It takes in some error between my temperature that it actually measured out and the temperature of my set point, and that goes into its own temperature controller itself. That leads me into an MV, or what would normally be the percent open that we need, and that is still true. That is going to tell me how much flow rate I need based on the actual process valve and what it should do to manipulate that specific variable. So that is going to go and take information in about the current position of that process valve. It's going to say, okay, well, what is the current flow rate happening? And should that be manipulated a little bit higher or lower to actually match the desired flow rate that would yield the temperature of interest? And we go, okay, well, that's going to have its own error function that needs to go into its own controller for the flow. That is going to lead into the process of my flow right here. That is then going to take in disturbance errors of the flow that might have just come in with it already and lead me out to my CV output. That will then be taken in information to go into the main process with its own disturbance and be read out. So we have an inner and an outer discussing the flow and the temperature, which ultimate goal is temperature. That is my primary goal in this situation. But we have multiple CVs that we're reading out in order to then go from the inner to the outer to relate that information. So how would we solve this? You probably guessed it, inner to the outer. So we're going to start with a secondary loop and move into the primary. So to begin, we're going to do secondary first. And to do that, we need to understand CV2 in relation to its own input variables. These would be MV1 or SP2, and CV2 related to DV2. Those are always going to maintain the same property, where it's always going to be based on the equation pi of my forward over 1 plus pi of my loop. And we can call this pi of E if we want, but this is essentially going to be everything based on the feedback loop. So that's going to maintain true. So then if we follow this, CV2 over SP2, which is the same as CV2 over MV1 because of the same thing, that is going to ultimately be equal to the forward, which is GC2 GP2 over 1 plus GC2 GP2 GM2. And my other, which is going to be CV2 over DV2, is going to be, that direction forward is the GD2 over 1 plus GC2, GP2, GM2. And that statement will be true for this expression. So we know that to define the stability of the inner loop, it's based on the bottom piece here, which will allow us to see stability and the conditions of which those will be true. So we can solve that, and we can then relate that back in, and now we have a way to observe how this process looks. This still has two pieces though. This still has its own input of the disturbance variable, as well as our input of the CV2 over SP2. But the good thing is when we rewrite that, we can actually relate that back down and distill it a little bit easier. So to form this, I'm going to redraw this, but let's take the inner loops. So we'll start with this piece of really the entire inside loop, which is now going to be my CV2 over MV2 expression. That is going to be then added with my disturbance expression, which is my CV2 over DV2, which comes from the DV2 input. Now this is going to directly go and yield out my CV2 based on my original input here, which was really my in this case, my set point or my MV. I meant to write 1, sorry. So full inner loop. We've just solved this piece and turned it into this. We have MV1 that comes in to a transfer function here that relates CV2 over MV1. That gets added to my other input, dV2, that relates the transfer function CV2 over dV2 that goes in as an addition function to yield CV2. And that makes sense, because CV2 is a function of both of these. Thus, all we're saying is CV2 is equal to dV2 times CV2 dV2, which is that component piece, plus MV1 times CV2 MV1, which is, again, CV2, the other piece. The two pieces come together to form the total CV2. So my feedback loop has been solved to this specific function. Great. We're going to use these later, so no fear. But we still have other pieces. Before this, we have a controller. We have GC1. After this, we have the full process, GP1. That process then has its own output, as here, which has its own adding of disturbance, which comes from GD1. That comes from DV1. That leads to my CV1 that has its own feedback into GM1. That leads into an error function that comes from the set point, makes an error that goes into my controller. So we have essentially turned this into this, and we can solve that. Really, if you look at it, all we've done is added this piece here in the center, but that is okay. We can solve for that directly. And so ultimately, when we're looking at this, we now want to define CV1 based on a couple of pieces. We're curious about what is the relationship of CV1 based on my SP1, my CV1 over my DV2, and my CV1 over DV1. And that's because in total, we have our output piece here, CV1, but it's based off of inputs, SP1, DV2, and DV1. So in total, we are establishing the relationship of my temperature control based off of our desired temperature input of set point that relates any type of error-based changes in my DV1, which is my initial temperature, and my initial flow rate that comes in based on my setting. So we are designing an inner controller that maintains a constant flow so that that value can be thought of as truly constant for us. But to this point, we've kind of just been assuming that if we say it's F, it's going to be F. And that can actually be true for a lot of these. There's flow rates here, there's flow rate here, there's changes in volume that might be happening by some leak in the tank. There's so many things that could be controlled that this is just supposed to be a representative example of how we can use these higher layers of control. But either way, this is still going to be based on the same ideas, that to solve any of these, like CV1 over SP1, that's equal to pi F over 1 plus pi E, or the multiplication of my transfer functions in the forward stage over 1 plus the multiplication of my transfer functions in the closed loop. So to solve any of these, that would be true. We would just follow the expression forward. So we move forward, we move forward, we move forward. Either way, we maintain establishing our relationship of our transfer functions to get the total CV. Because truly, at the end of the day, to get CV1, this is equal to SP1 times CV1 over SP1 plus DV2 times CV1 over DV2 plus DV1 times CV1 over DV1. And this should feel familiar. This should feel exactly like thermo, where you hold some values constant, where here we're really thinking about establishing these to be regardless of the DV1 and DV2 condition. This is regardless of SP1 and DV1, and so forth for the last, regardless of SP1 and DV1, I'm sorry, 2. And that is going to yield our total expression based on these inner transfer functions that exist in our system. So to solve for these, it's done the exact same way. One of them I could do as a representative example, where that one would become, say we did my CV1 over SP1, then in this case, I'll write it down here because I have a little bit of room. CV1 over SP1 would then become, think of the whole expression forward. So this is going to be GC1 times CV2 over MV1 times GP1. And that's it. On the bottom, 1 plus the elements of the loop. So that would be the same piece as the GC1, the MV1 based on CV1 from 2, times GP1 times GM1. And that would be the inner loop. So the stability of the full expression would then be satisfied by this piece. So we would want to solve for when that equals 0. So then to get the stability of everything, we would want to plug in for CV2 over MV1 there, which we can do. I don't really have any room, but what I can do is erase this piece to allow for that. So if I do that, you're seeing the secret that erasing is a little challenging on these boards. It takes a lot of muscle, a lot of elbow grease. So what I can do is, based on this bottom expression, our stability criteria of the loop is when 0 equals 1 plus pi e. And so we want to solve for when 0 equals this. So that, if I plug in for the other piece of expression right here, that would become 0 equals 1 plus GC1 times GP1 times GM1 times the CV2 over MV1 expression, which is GC2 GP2 over 1 plus GC2 GP2 GM2. So now we have GC2, GP2, GC1, GP1, GM1 all over 1 plus GC2, GP2, GM2. What I can do is I can multiply everything by essentially a piece that would escape that here so that we can multiply through by it all. To do that, I'm going to multiply everything by the denominator. So I'm going to multiply everything by 1 plus GC2, GP2, GM2 over 1 plus GC2, GP2, GM2. That's going to negate the bottom piece here, and I'm going to expand that top piece now over here, where in total, I'm now going to get a closed-loop criteria of 0 equals, ultimately at the end, 1 plus GC2, GP2, GM2, plus GC1, GC2, GP1, GP2, GM1. And that will be the solution to my stability criteria, which is just really the characteristic equation of the denominator here for my total solution. And that bottom piece will be exemplified in every one of these. It would be in the GD1, the dV1, the dV2 expressions, but this is my stability characteristic equation. And so in total, my characteristic equation is now just built off of more pieces. And if you notice, it's built primarily off of my GP2, GC2, GM2, and then a combination of the first and second controller with the first and second process, and so forth. And that this does help to establish some type of interesting relationship that for one piece of stability, it's entirely based on the inner loop. So that inner loop is fast. It allows you to reach some form of stability, but then we can compensate stability related on the first controller to the second controller, the first process to the second process. And that's actually really unique to think about. So we can offset some of those characteristic values if they might be at an edge of stability for our primary controller, GC1, based off of the characteristics of GC2. So pretty cool. We are gaining a more interesting element of control, but we are distributing decision-making within our controller system. So there's really no limit to the number of Cascade levels that you can have. You can have multiple levels involved. They can be 3, 4, 5, But ultimately, we're trying to think about how to build a fast type of controller response where our inner controllers are quick and can make fast round decisions to maintain elements of control and stability on the outside. So if we added more layers to this, that would be great, but we're going to be decreasing how often, therefore, we need to change our TC based on the fact that FC is changing a lot and very, very fast. So food for thought to consider with control theory, but ultimately, this is what we want to get to. This is the goal. We've arrived. We've reached it. We thought about control theory from first principles of how would we design a stirred tank reactor that is safe, and how can we use safety and process simulation together to come to this consensus that we can design wildly complex systems, but still think of first principles of former classes like thermodynamics in order to solve this. And at the end of the day, we could do it with really sophisticated means, and it's pretty cool to see what we can reach. So hopefully this has been fun. And I really hope that you just had a great time. So I will see you all soon. Hope you have a wonderful day.